We're in section 5.4, optimization. Here we're going to apply what we learned about local and absolute maxes and mins and apply them to situations where we want to find a value of x that optimizes a function, meaning that we maximize or minimize the function. Now, although we're often finding the absolute maxes and mins, and so here's a quick refresher for how to do that, a lot of times we use the same techniques that we did to find local maxes and mins, in particular the first derivative test, right? So a lot of times what happens is if we have a situation where we take the first derivative, we set it equal to 0, and we find one critical number, and we have a situation where the interval chart looks like that, then we know not only is f of c a local max, but it's also an absolute maximum, right? And that should make sense, right? Because if the function is increasing before c and then decreasing after c, then the function can't get any bigger than that, right? So, I mean, really, it would probably look something like that, but there you go. All right, and of course, analogously, if we have the opposite, where a function is decreasing and then increasing before and after a critical number, then not only do we have a local minimum, we have an absolute minimum. Okay, and we're just going to keep this in mind. This will help us with our optimization problems. Now, for some of these problems, they are a bit geometric, and they involve optimizing the area or perimeter or whatever of a certain shape. And so when that happens, it's often good to draw a picture. If you want to pause and read example 1, you'll see that we have a situation where we want to make a rectangular fence, or maybe it's a square, who knows, but at the very least it's rectangular. And the wrinkle with this problem is that, well, it's up against this river. So we really need only 3 sides of this fence. We need to use only 3 sides of fencing material. The 4th side will be the river, okay? And we want to maximize the area, right? We can see that. What are the dimensions that have the largest area? Now, I drew a generic picture, right? I don't know what this fence looks like. Maybe it's a bit more squarish or something like that. Maybe it's very tall. I don't know. But I just drew a generic picture like this. And because we want to know the dimensions of the field, right, maybe it would be good if I just labeled my sides as, well, I guess this will be the length, and this is the width. And maybe I'll just point out that this is the width. This is not the length right here because we're not using fencing material. So I'm not going to label it. Okay? And so note that based on the problem, we are trying to maximize the area of this rectangle, which is the length times the width. But you also might notice that L and W are 2 variables, and so we can't just take the derivative of that and set it equal to 0 because we don't know how to differentiate functions with 2 variables. So in addition to this function, this area function that's being maximized, we also have something called the constraint, which is an equation that restricts our numbers and is going to allow us to substitute in for one of the variables. So in this case, we want to maximize the area of a rectangle. So our first equation is going to be A equals length times width, right? No surprises there. Just look at the picture, right? Now, what's the restriction on the fencing? Well, they say that we have 2,400 feet of fencing and we have 3 sides. So if we add the 3 sides together, we get L plus 2W equals 2,400. See how we get that? That is the constraint on our fence. So what we're going to do is we're going to use the constraint to solve for L, then substitute L into A equals LW, right? So we have that L plus 2W equals 2,400, right? That was our constraint, and that's going to imply that L equals 2,400 minus 2W, And that means then that area, which equals L times W, actually equals 2400 minus 2W times W. See what we did there? We just substituted in L equals 2400 minus 2W in for L, right? See that right there. And then, of course, we can, if I could squeeze this in a little bit more, just move it up a little bit more, just so I can point out that this really equals 2400 W minus 2W squared, right? Now that A is in terms of one variable, right, just W, we can take the derivative, set it equal to 0. Okay? So let's do that. A prime of W is going to equal 2400 minus 4W, right? Set equal to 0, and we find that W equals 600. And now quickly we want to test out our answer, right? We want to make sure that we do in fact have a maximum and not a minimum. Now we do want to keep in mind that W needs to be greater than 0, right, for our purposes. Otherwise the rectangular fence wouldn't really make sense. But for our purposes, we can plug in any value less than 600, right? So if we plug in W equals 0, we're going to get a positive value for A prime. Plug in a number like, I don't know, 700, you get a negative. So good. We do, in fact, have a maximum here. So we can just say A is maxed at W equals 600 feet. I think it was 600 feet, right? Yeah, feet. Okay. Now, this is the last part of it, though, right? We need to answer the question. They say, what are the dimensions of the fence of the largest area? They didn't ask for the largest area. They asked for the dimensions. Well, that means we need to find L. And if L equals 2400 minus 2W, then that's going to equal 2400 minus 2 times 600, and that equals 1200 feet. So the dimensions that maximize area are 1200 feet by 600 feet. Okay, so that's how you do that one. Here's another example. Here we have a box, we have 1,200 square centimeters of material available. And the reason we're squaring those centimeters is because we have just, that's the surface area of our cardboard, right? It's like a big sheet of cardboard or something like that, right? And the question is, how do we make a box with a square base and an open top? So it's a little bit of a wrinkle. And we want to find the largest possible volume of the box. Okay, well, first off, again, draw a picture. I will, again, use brown, as boxes are typically brown. And maybe I should make that base a little more square looking, right? Anyway, do that. And then maybe, this. We don't know how high this box goes, so I'm just say that's a bit taller. Something like that, and just maybe color it in just to emphasize that we have an open top. Maybe I'll use black or gray, how about, right? Has an open top, right? Open top. All right, anyway, so what are we trying to do? We want to maximize the volume. Well, if we let this be S, we know that the bottom has a square base, so it's S and S on the bottom. And I'll call this H for height. So we have volume equals S squared H. So what's the constraint then? Well, the constraint, yes, it is going to involve a 1200. It's good if you saw that. But it's going to be the surface area of the cardboard, right? You don't even need to write this A equals. I just want to point out that we're using the surface area formula. And in this case, it's going to be, let me see if I can get a highlighter to properly, right? S squared, right? Where are we getting that? S squared is from that brown part, right? That bottom of the box. Plus, and let's see what we've got. Maybe I'll use this to sketch, right? 1, right, this right side here, 2, the back side, 3, the left side, and 4, this front side, right? And the area of each of those sides is SH, and there are 4 of them, so we have S squared plus 4SH. And that equals 1200, okay? So if we solve for H, then we get 4SH equals 1200 minus S squared. Solve for H, divide by 4S, and we get our answer. Or not our answer, but our substitution for H. Right? So that means that V, which equals S squared H, actually equals S squared times this lovely guy. Right, see, we just substituted in for H. Right, and now, of course, it's better to simplify now to make the derivative as easy as possible than to, like, do a quotient rule and a product rule and all that nonsense, right? So anyway, we're going to get, I think it's 300S minus S cubed over 4. Okay? So now, again, V is just a function of S, and so we find V prime of S, which is going to equal 300 minus 3/4 S squared, and we set that equal to 0. And we're going to multiply each side by 4/3. So the 3/4 is going to go to 1. 300 goes to 400. And we have 400 minus S squared equals 0. If you can see the factorization, that's great. If not, then multiply both sides by -1. And you get S squared minus 400 equals 0. And that implies S plus 20 times S minus 20 equals 0. And that implies that S equals minus 20 and 20. But of course, -20 is not a thing. We can't have a side of negative length. So we're really just concerned with 20, right? Now let's quickly make sure that we do, in fact, have a max. And again, we should, right? So if we plug in 0 in for S right into here, we're going to get a positive. Plug in, I don't know, 100, right? You're going to get a negative. So V is maxed, very formal, at S equals 20, S equals 20 centimeters. Okay, and note that we're using just centimeters because we're talking about length, not area or volume. Okay, now let's just be careful, right? They want to know the maximum volume, right? Largest possible volume. So you could do two things. You could plug S back into H, into the constraint equation for H, and then do S squared times that. Or you can just say, so the maximum volume of the box is, what is it? Actually, it's going to be V equals 300 times 20 minus 20 cubed over 4. And if you simplify this out, you wind up getting 6,000 minus 8,000 over 4. And that's 6,000 minus 2,000. And that equals 4,000. And we should use units. It's going to be centimeters cubed because it's volume. Volume's 3-dimensional. Okay. So we're done with that problem. So that's all for right now.